Okay, thank you, Fabien, and thank you all the organizers for this very stimulating conference. And for an obvious reason, I'm very glad that this conference takes place here in Cargese. And thank you to all of you to be here. It's always hard to wake up early in the morning, the day after the barbecue party, but it's also challenging to be the first speaker after this. So today I have the ambition to bring a very modest contribution to the glory of localization landscape theory. And namely, I want to show you how to extend this theory to tight bending system. And I put here microwave into parentheses because the main impetus of this work a few years ago came from my interest, our interest in my group in Nice, and I will humbly say our expertise in microwave experiments. And I'm going to show you how, starting from microwave experiments, progressively we hand to tight bending Hamiltonian, to localization landscape in tight bending Hamiltonian. But okay, and just a word that most of the results I'm going to present are due to this guy, Alberto, during this PhD thesis. So if something wrong, it's his fault. So, okay, so let's start with the... Okay, sorry. So let's start with the experiment. So the main ingredient in the experiment I drive in Nice is this centimeter size dielectric cylinders made of this. I don't even try to pronounce this, but okay, it's written. And the interest for us is that this material has a very high permittivity, up to 45. It means optical index higher than 6, and reasonably low loss. And this, we can put these cylinders in a design way, very precisely controlled, and we put a top plates tightly screwed, and we can excite. There is a fixed dipolar antenna here, and we can excite and probe the field inside the cavity by this moving dipolar antenna. We generate a TM polarization, and just to be sure, for me TM means you have a dipolar antenna in this direction, so I excite the electric field polarized in this direction, and I have several modes to play with. And in the experiment I'm going to show you the results. We will stay focused to a TM0 mode, or the electric field is constant in the Z direction, and it means that we stay below the cutoff frequency of the appearance of the TM1 mode. And everything is controlled by what is called a vector network analyzer, but for a physicist, this device is simply something which gives you the full and complex scattering matrix with the two reflection by the two ports, two antenna, and the two transmission. And we can, if we need to simulate an open system in the plane, we can put some absorptive foam on the boundary. And one of the main interests of this experiment is that we have a perfect control, as I told you, of the disorder. So we were interested 2 years ago in the ambition to control the transport property just by playing with the spatial correlation of the disorder. Somehow the objective was, the three main regime of transport in a media. The transport is either ballistic or diffusive, or even can be no transport at all if the energy of the particle, of the frequency of the wave falls inside the band gap. And our objective was to bring together all this regime of propagation in a single lattice, in a single medial, without changing too much frequency. And this, for achieve this goal, we play with what is called the stealthy hyperuniform disordered lattice. So forget the jargon, but what is important in this hyperuniform device is that you have a system which exhibits correlation at disorder at short range, but correlation at long range. You have a disordered system, but without any density fluctuation at large scales. And you have a parameter called usually chi, which control the degree of correlation. The smaller, this parameter is comprised between 0 and 1. The smaller this parameter, the higher the disorder at short range, and the larger, close to 1. In practice, it never reach 1 because you have a crystallization around the 0.6, 0.5. And for large value of chi, you are close to periodic lattice. And this is absolutely not an artificial strategy, because in nature, this strategy is developed. For example, this is a macroscopic view of the fibrin collagen, which are distributed according hyperuniform lattice. And this is reproducible for the blue color of the nerves of the mandrill. And here you see the structure factor of this distribution. I recall here the definition of the structure factor, which is essentially the spatial Fourier transform of the position of the scatterer, here the collagen, and you have this very specific behavior of structure factor with a region near the origin without any diffusion. And you have the same strategy in the feather of this kingfisher, and here you see the microscopic view of the very tortuous structure of the feather. So in nature, this colorful strategy belongs to a strategy of seduction, and the goal of breeding is explicit for the vervet monkey, but I don't want to enter into detail. So let's focus on physics. So we have this hyperuniform system with a control of correlation, and here is a radial structure factor depending on the degree of correlation. So you see that here, for a high value of the parameter chi, you have a structure factor which looks like a crystal. Here, the straight line represents the structure factor of triangular lattice. And for smaller chi, progressively the peak vanishes, and you have the structure factor almost flat. And the point I want to stress out is that the individual, all the scatterer have the same individual property, is this scattering cross-section of a single cylinder with the first 2 Mi resonance, the two TM0 Mi resonance, but this one is the S wave, and here is the P wave, and so on. And what is important, in the frequency range we will use for the measurement, you see that this curve is the ratio between the typical size of the system and the scattering cross-section. And you see that this curve is almost flat along all the frequency range, and with a value close to 100. Okay, and just to precise that for whatever the distribution, the degree of correlation, the density is exactly the same. And what we obtain, I could show a lot of results, but I focus on the quantity that you know, is the tailless conductance. And what we see, there is an extra factor 10 just to, for the sake of clarity, but you see that the tailless conductance exhibits different behavior with a drastic drop near a gap which appears and which become larger and larger as far as the correlation increase, and even the appearance of a second gap at higher energy for the largest correlated system. And we can image. Because I can okay. I wanted to skip. I have a slide, but I wanted to not to spend too much time. But essentially, we have access in these experiments to all the individual resonance which build the transmission. So we can write the transmission signal in the Bright-Wigner formula with the sum of our complex Lorentzian, and we have access of the 4 parameters of the complex resonance. Frequency, amplitude, phase, and decay rate. So with this, we can build with the width and the frequency, we can build step by step, and the density of states, we can build the tailless conductance. So exactly. And if we simulate, because we have access to stationary measurements, but everything is linear, so we can mimic pulse spreading. And here it's depending on the central frequency of a Gaussian excitation, we see that we have different regime of propagation. This is a stealth regime when you see that even the fact that the scattering is strong and the density is the same setup, the same disorder, then here you have a completely ballistic propagation. At the end, the time evolves in this direction. At the end, it becomes blurred because you have the reflection, the small reflection of the absorptive form, which are not completely absorptive. And you have the diffusive regime in this domain and this domain. And below and above the gap, you have the two localization region. So I know this is a 2D system, so it is supposed to be fully localized, but it's finite system, and the correlation can change drastically the localization length and the behavior, and we see clearly these three different regimes. Okay, so there is another, we play with another type of correlation and see if it was not the case yesterday, the poster put by Alberto when you use quasi-periodic system in a Fogel spiral. So, as I told you, so it was, we have experiment when we have a single realization of disorder. We have several type of behavior of mode. So it's a playground, a natural playground for the landscape theory. So we try, naively maybe, to develop a localization landscape for electromagnetic waves. So let me briefly recall what is the localization landscape for the Schrödinger equation. So you start with the usual Schrödinger equation. The localization landscape is defined in this way, and you obtain, just by the change of variable, you obtain this new equation where one of you plays the role of a confining potential. And effectively, if you perform a simulation, you and use this kind of disorder, and here I plot the first four eigenstates of this Hamiltonian, and here the first minimum value of 1 over u, and you have a perfect agreement between the position of the minima and the position of the eigenstates, and so on. Okay, let's do the same for the Helmholtz equation. So we have this equation. Just one point. What is important in the localization landscape theory is to deal with Hermitian operator. This operator is not Hermitian, so the proper way to rewrite the Helmholtz equation is in this way. You define this ancillary quantity, and you define a new operator L, and this operator is Hermitian, and you have to play with this operator to develop. But the problem is not really here in the way we read. The problem is that it's a vectorial equation, and for the moment, it's a nightmare, and up to now, I speak under the control of the master, but there is no solution to the vectorial equation. Okay, it's not a crude limitation because our experiments are 2D with a fixed polarization. So in fact, we play with 2D scalar equation. So I can rewrite the equation without any free charge or free current. And this equation we have to deal with is this one. And in this case, I could also write here invoking an Hermitian operator, but I maintain the usual way to write it. And in this case, the definition of the localization landscape is slightly different. It's not the operator applied to u equal 1, but equal epsilon of R, the variable permittivity. And in this case, when you define the localization landscape in this way, 1 over u, if you put this use this change of variable, you end up with an equation which is strictly equivalent to the one obtained in the Schrödinger's case. So once again, you have 1 over u, it's an effective confining potential, and that's the end of the story. Thank you for your attention. Not really, because okay, it's an effective confining potential, but it's a completely useless confining potential. And why? Because here I plot 1 over u, and what we see, it's a square well. Okay, it's a confining potential, and that's true that the first mode eigenstates of this of the Hamiltonian can be described by this square dip, but it's not really what interests us. We are interested, much more interested, to describe with the strategy of localization landscape the complex localized mode. But the localized mode in this case are not at low energy where we can easily measure the minima, but the localized mode at high energy. And this is, and so okay, we have a landscape, but it's not very interesting. And this effect is not really a surprise because here I rewrite the Helmholtz equation for the TM polarization for the TM polarization in a Schrödinger-like form. Okay, just I put on left and right, and what you see that's the potential. We have the omega square in factor. So it means that at low frequency there is no potential, and this is exactly no potential seen by the wave, and this is exactly what we see. Okay. So for the TM polarization, for the moment, we end up to the dead end, but we will see in the future. But we can switch. In our experiments, we can easily change the polarization and work with the TE polarization. So in this case, the TE polarization, now we use as excitation. So it's the same. Sorry, it's the same. Dielectric material, almost the same setup, but the main difference is the excitation. Now we use either what I call a kink antenna or a loop antenna. And this kind of antenna placed between the two plates excites the Z component of the magnetic field. And in this case, due to the fact that the boundary conditions are not the same for the electric and the magnetic field, there is no TM0 mode. The magnetic field cannot be constant. So you have a TE1 mode with arch of sinus between the plate, and the TE2 mode with a node in the middle. And we have two cutoff frequency. And you have one cutoff frequency also for the lowest mode. And it means that we can play, and the cutoff frequency is controlled by the index of the medium. So by adjusting the size between the plates, we can have a situation where we have below the cutoff frequency in the air and above the cutoff frequency in the material. And in this case, we are in fact implementing a time bending system. Why? Because here I show you the S mode of the first T resonance. This is a view from the top of the magnetic field inside, and here is a profile along this direction. And essentially, so the Z component is simple, is this arch of sinus, and inside the material you have a G0 Bissell function, and outside, since you are below the cutoff, you have a K0 Bissell function, and the K0 of gamma r is essentially exponential minus gamma r divided by square root of gamma r. So it's essentially exponentially decaying. So we have a sort of Lego, and we can play of molecular and condensed matter physics with this centimeter size cylinder. So I show you what happens when I put close together two resonators. We have two modes, an antisymmetric and a symmetric, and two peaks in the spectrum. And depending on the distance, the splitting is not the same, and we have this law of coupling depending on the distance, and this is exactly given by a naive time-bending model with the same bare frequency and the coupling on the diagonal. And we play a lot with this because we have almost no limitation of the pattern we can design. So, for example, I show you a very simple, just to show you what we are able to measure by reflection measurement. So we have this movable top plate with a loop antenna in the middle, and we can probe the field at the top of each resonator. And in reflection, we obtain essentially, we can build on a given frequency range the local density of states for a fixed position, and by averaging the density of states. And we can also, if we fix the frequency, we can also, by moving the position, we can build the intensity of the eigenstates. And from transmission measurement, from a fixed antenna to the movable one, we have access to the phase, amplitude and the phase of the eigenstate, and we can simulate pulse spreading. Here I show you some results in a benzene, artificial benzene molecule, but we did it in a lot of lattice. Just a few pictures. We were one of the first team to observe in artificial graphene the topological phase transition, which can be obtained when you strain uniformly along a crystalline axis the graphene. For us, the graphene just an Honeycomb lattice of a resonator. We study carefully with a very nice collaboration with Gilles Montambeau all the effects of the canonical H states in a graphene ribbon. We study also this work was done in collaboration with Patrizia Vignolo. We study we measure for the first time the gap labeling theory in a Penrose lattice, and more recently we develop an experiment on a Fibonacci chain with variable increasing length, and we show the multifractality of, it cannot be seen here, but we show the multifractality of the wave function which can be measured in this system. And recently also, we were able to generate a gigantic pseudo-magnetic field in a non-homogeneously strained Honeycomb lattice. And I know that there is people from Grenoble and Toulouse in the audience. So the place in France were supposed to generate high-intense magnetic field, but 42,000 Tesla. Okay, it's pseudo. But that's more interesting that we were able to follow the continuous deformation from a topological H state to a fully developed Landau level. And all this thing was doing respecting the sublattice polarization, which is a smoking gun of topological effect in this kind of system. Okay, but I have no time to enter into this. So now the objective is to develop a localization landscape for tight bending system. So previously, Svitlana and Marcel, with this collaborator, obtained results for 1D system, and the main results of this paper was to prove the existence in 1D of a pair of discrete dual landscape at low and also at high energy. And more recently, in a paper cited by Svitlana during his talk, two guys, Wang and Zhang, if I'm not okay, prove that the inverse of this discrete landscape play also the role of confining a discrete confining potential. Okay, so we start with 2D tight bending Hamiltonian. I wrote here not in the usual way, but it's the same. There is an extra time which can disappear here, but I wrote it in this way in order to show the difference between the discrete Laplacian form and the potential term. Okay, so I can induce the disorder in this way. W is the strength, and U is the random variable. Okay, so let's start with the lattice we like to play with. It's a Honeycomb lattice. So everybody knows, I guess, the property of this lattice. It's a triangular lattice with two atom per unit cell. is dispersion relation is celebrated due to the famous Dirac point and the playground for relativistic physics and interesting topological physics, and so on. So, okay, everything is well known. So we simulate in this lattice a disorder potential of this kind, and what we obtain here, I plot depending on the energy, the IPR of the eigenstates, and I recall here the definition of the IPR for the eigenstates J is for a discrete system is essentially the ratio between the modulus 4 of this of the amplitude divided by the square of the modulus square. Okay, and it's a mark of the localization. Close to 1, you have a well-localized system, and when it tends to 0, we have a delocalized system. And what we observe, it was known, you have 2 sets of localized states, one at low energy. Here I plot the first 4 eigenstates, and here the last 4 eigenstates, and we see well-localized eigenstates for the low energy with a smooth behavior in a small region. And on the contrary, for the high energy states, we have a very rapidly oscillating amplitude, because you know that the amplitude changes sign from one side to the other. Okay, furthermore, let's stay focused on the low energy, usual low energy localized modes. So we can easily calculate the localization landscape by calculating H2 equal 1. And what we obtain in this, it's a problem with discrete, you obtain nice picture because I cannot smooth. The yellow light color is the minima, and we see here the minima, the 4 first minima of the localization, of the inverse of the localization landscape. If I compare, by eyes is not obvious, but we compare it very carefully numerically, and here the basin are the same. And once again, as was observed in the continuous setting, the minima of this of 1 over u gives the position of the eigenstate. Alors the agreement is not always the same. The order is not always the same. I order it by value of minima, but this is not an issue. This is also observed in a continuous case, and is not important. What is important for the localization landscape is that the lowest minima gives the position of the lowest eigenstate. And this is always observed. And I will show you at the end that this small mismatch or switch is not a problem for a quantity of interest in physics. Okay, so now we have to address the localization landscape for the high energy eigenstate. So we tried different strategy. We use a comparison matrix defined by Carlo yesterday, and even the L-square landscape, but we obtained nothing with really convincing. And once we realize that, and this, I'm going to address a question raised by Denise during Svitlana talks, that we forgot that we have some specific symmetry in this system, and this symmetry will help us to build correctly the high energy localization landscape. Okay, for the Honeycomb lattice, without disorder, we have the well-known symmetry, which is called the chiral symmetry. If I define this operator, which is a poly-like operator, but which is defined as the difference of the projector on the A side minus the projector of the B side. So why it's called a sigma z operator? Because if you have in mind in the block representation of the 2 sublattices A and B, this operator is 1 minus 1. So it is why we call it sigma z. And this is a chiral anti-symmetry, well known for this system, which is responsible for the symmetry of the band. And only topological H states appear at 0 energy and break this symmetry. This is why the topological H states are sublattice polarized. Okay, so this is the situation without any disorder. Of course, if you put disorder, you break this symmetry, and this is one example of the density of state in the presence of moderate disorder, and we break immediately the symmetry. Okay. We break the symmetry, but the disorder is a diagonal disorder, so it means that it remains a relation which is helpful, is that if you apply this to the operator, the complete operator, in fact you have this relation, that the application of sigma z change, in fact, the sign of the on-site energy. And this is exactly what we observe. For the same realization of disorder, we just invert the sign. It's not a new simulation with a new disorder. It's the same disorder, but we invert the sign. And what we see is that it inverts the bond. So the strategy now is clear. What we have to do to build the high energy landscape for the original problem. First, we create a new Hamiltonian with a band inversion. And then we calculate, so this Hamiltonian is defined in this way. Here I put a shift, a V shift, just in order to keep a positive definite Hamiltonian, but just a reference, it doesn't change anything. And now the lowest eigenstates of this new Hamiltonian have a relation with the highest eigenstate of the original. And what is the relation? Very elementary school algebra show that this new eigenstates are simply the image through this operator of the original one with E minus E. So it means that phi give a demodulated version of the high energy eigenstate. And when I compare the original high energy eigenstates with the oscillating amplitude, I know that the lowest one are exactly at the same site, exactly at the symmetric energy, exactly at the same site. But since we apply sigma z, which inverse the sign of one of the two lattices, we observe something which is uniform. So a smooth, low energy eigenstate. So that's the end of the story, because we build the landscape for this new low energy eigenstate, and we will have solved the high energy problem. And this is exactly what we did. So we calculate the landscape associated to this operator, which can be considered as the dual version of the original one, which is high energy for the original problem. And we obtain basin in this landscape exactly as the position of the original eigenstate. Okay, so this is for the position of the eigenstate, but we can do better. We can even, better, I don't know if it is better, we can do more. We can try to calculate the eigenvalues, to predict the eigenvalues. There is a prediction a fact in the continuous case that the eigenvalues are directly proportional to the minima of the confining potential, with proportionality driven by depending on the dimension. So for 2D is 1.5. Okay. Okay, so let's say if we have this kind of relation in a discrete system. So here I plot the minimum of 1 over u for low energy, of 1 over u star for high energy, of the versus the eigenvalues. Okay, and in blue, in blue is for the 3% lowest eigenvalues and minima. In orange for the tier between 3 and 5%, and in pink between 5 and 7%. And what we see that for the lowest and the highest, we have a perfect proportionality with a Pearson coefficient very close to 1. So it means that this kind of relation holds, and in this case with the low disorder, the coefficient of proportionality is close to what is expected for continuous case. So we perform an exhaustive study, And we change a little bit because now I'm going to show you results obtained with another lattice, we not stay focused on Honeycomb. So I change slightly the definition, how I quantify the disorder, not by W, because W, if I change the lattice, I change the connectivity in the second term, so I change the effective strength of the disorder. So to have an ubiquitous quantity to measure the disorder, we use the mean IP here. In this way, we can compare different lattice with different connectivity, different nearest neighbor interaction. Okay. But first, this is what we obtained for the Honeycomb lattice. This point is the situation shown here. And to all these points, we obtain the same quality of proportionality with something which, in the strong disorder limits, which is close to 1 and is not too complicated to guess this value, because in the very strong disorder limit, the eigenstates are localized on a single site. So we have essentially this relation, which means that 1 over u is proportional to the energy, and the slope is 1. Okay. In the weak disorder limit, somehow we expect that we have just an approximation of discrete approximation of the continuous situation, and we should have something close, not strictly equal. Is not a clear-cut argument, it's just a hand-wave argument, but we are close to the continuous, and this is what we observe with the Honeycomb. But now I plot different lattice we test in 1D, a regular chain. Dimerization. All these lattices bear the same property, that share the same property, that they have a symmetric and they respect the symmetry I mentioned at the beginning for the Honeycomb. So there's a chain, the dimer in 1D, the square lattice, and the Lieb lattice. The Lieb lattice is essentially a square lattice with a third atom in a unit cell, and you have 3 bands. 2 symmetric bands with 1 direct point and a flat band at 0 energy. And in all the cases, what we can see is that it seems to have a master curve with slight difference depending on the dimension of the system. So it converges to the continuous case for 1D and here for 2D. With, okay, there is a deviance for the Lieb lattice, but once again, what is important is not the precise value. What is important is to have a proportionality. And I will show you the integrated density of state at the end of my talk, and for all this lattice, it works. Okay, so now we have a strategy based on the symmetry of the system for the Honeycomb and all this bipartite lattice. But what happens when the symmetry is not present? And for example, what happens for the triangular or hexagonal? There is a fight in my group because I like to call this triangular lattice, and my close colleague Geoffroy Aubery call it hexagonal lattice. So, depending, so I prefer triangular lattice. Okay, but and in this case, the dispersion relation is not symmetric. Okay, so what can be the strategy? There is no symmetry, but nevertheless there is particular point because for this I forgot the low energy landscape because it works well. We have no problem with the same quality, so I focus on the high energy. Okay, and what we observe in this case is once again the high energy eigenstates are highly oscillating and okay. So what could be the strategy? Okay, we have no global symmetry, but we have a specific point in the dispersion relation, which are the points where the energy is maximal. So what we try to do is to locate this maxima and to have a demodulation procedure based upon the value of this Kmax. Okay, so we define a new variable, a new eigenstate, which is a demodulated version of the original one. Okay, if we do this, we obtain this kind of Hamiltonian. And so with this kind of Hamiltonian, for short, I call it H star, which has this complex, complicated and complex in the non-real sense expression. And we have this new equation, and we can solve the confining potential. The new situation is now the confining potential is complex. Okay, but what happens is that the modulus appears to play exactly the same role as the original real landscape for the symmetric situation. See, here I plot the minima of one of modulus of U star, and you see the position of the last four eigenstates and the minima of 1 over U star. So it works well. We have also the same quality of proportionality for the low energy and the high energy situation. In this case, in the low disorder limits, the value for the continuous setting is not reached. Well, okay. And we try for several other lattice, not symmetric. This one, I don't know if all of you know this lattice. We try a more complicated lattice. The TTS is this weird lattice with 4 atoms per unit cell, and it works. It's almost undistinguishable from the hexagonal. Here is behave similarly, not exactly in the same way, but similarly. And the only the only weird result to obtain was obtained with the Kagome lattice, not at low energy, but at high energy when we apply the demodulation procedure, because we see this curve. But even if this curve is weird, the proportionality remains of good quality. But here we suspect, so the Kagome lattice is this lattice with 3 atoms per unit cell, 3 bands. And the problem is that the third band, the flat band, is on the top of the energy. So it means that the demodulation is spoiled, we guess, by this flat band. But anyway, whatever the slope of this curve, if we build the integrated density of states, or the cumulative number, here at low energy and at high energy, we obtain, I plot for the hexagonal lattice, but it's the same for all this kind of lattice. We obtain a very good approximation. I don't know what, the eigenenergy is in blue, and the minima, the cumulative function built with the minima of the confining potential is in orange. And we obtain something which is a very good approximation at low and at high energy. And I didn't show for the symmetric lattice, but I show now. It works also extremely well. So we have some question still to solve with this flat band, but in general, the method applies very well for this tie bending situation. And there are maybe 2 challenges. There are most of young people here, very active and clever. So there is no money at all, just for the fun. So there are 2 challenges. One theoretical one. The question is here: how to build a true localization landscape for electromagnetic wave. The problem, I can rephrase the problem I mentioned already. The problem is that in this situation, the term 1 of U is useless. So it means that we have, Marcel and his brilliant mathematician colleagues has to think about how to build a localization landscape, a new way to interpret the kinetic part. And if this problem in the scalar case is solved, it means that we will play with a div grad operator, and it means it will give hints to solve the complete vectorial problem. Okay, but I guess there is stuff. I finished. And there is a last experimental challenge. It was the original, the idea we had a couple of years ago is to measure directly the electromagnetic landscape. A measure of the landscape has been done for classical wave and scalar wave in the elastodynamic situation, an experiment done by Patrick Seba, where they measure a static deformation of a thin plate. And this, by measuring the static deformations, they were able to directly measure the localization landscape, and it was effectively the well where the eigenstates were stuck when they measure it. And we tried to imagine how to perform the equivalent for the electromagnetic well, and for the moment we failed. Okay, let me just present my collaborator. For the multiple transport regime, we work a lot with Frank Sheffold and with Froof. And Geoffroy Auvry is a driving force of all this project. And I already mentioned Alberto. And of course, for the localization, we collaborate with Captain Philoche. And thank you.